Hi, my name is Erik Thordsen from TU Dortmund University, and I welcome you to my talk on angle-based intrinsic dimensionality, which is in collaboration with Erich Schubert. First of all, I want to introduce you to the concept of intrinsic dimensionality. The dimensionality of a dataset is often denoted by the number of features. If we look at these two plots, we can see that each point from these sets is described by 3 coordinates. However, the two datasets clearly span intrinsically different subspaces. This idea gives rise to the term of intrinsic dimensionality, which is the number of parameters required to describe a dataset. In these examples, it would be 1 or 2 respectively, which is indicated by the grid lines. To further differentiate the terms, the number of features is called the representation dimensionality in this context. Where the intrinsic dimensionality is supposed to be the minimal and innate number of parameters that are required to fully discriminate between any points in the dataset, the representation dimensionality is the number of features that we observe. Even though the intrinsic dimensionality could theoretically be larger than the representation dimensionality, it is in most cases assumed to be smaller, since additional dimensions would need to be made up. In the case of linear subspaces like the 2 examples, the intrinsic dimensionality can be estimated by classical approaches like primal component analysis. However, if our dataset does not span a linear subspace, these approaches fail. Further, the intrinsic dimensionality might be locally dependent. If, for example, the region of interest in parameter space contracts to a line, or if we consider a mixture of different intrinsically dimensional datasets. The problem of intrinsic dimensionality estimation is hence to find the dimensionality of the parameter space that generates our dataset. That, of course, is only reasonable if we assume our data to be generated by a process like this and require certain assumptions on the embedding function and data distribution, which will be discussed later. To summarize, we assume that our observed data is a noisy embedding of samples in some parameter space. The goal of intrinsic dimensionality estimation is solely to find the dimensionality of the parameter space, not to find an embedding function. For the estimation to work, we expect both the embedding and the distribution of points in parameter space to follow certain assumptions. The problem of intrinsic dimensionality estimation has both theoretical and practical applications. Intrinsic dimensionality has been shown to be a better indicator for data complexity than the mere number of features. As many tasks, like k-nearest neighbor search, are largely dependent on data complexity, analysis and experimental setup should account for it. In these cases, intrinsic dimensionality can be a useful tool to adjust evaluations of, for example, algorithm performance. As local intrinsic dimensionality varies on a per-point basis, extremal behavior, like inexplicably high or low intrinsic dimensionality, can be used to identify outliers or noise. In the case of an entire set of unrelated noise points, these can be considered an overlapping high-dimensional manifold and identified with local intrinsic dimensionality estimation. Further, approaches like autoencoders in manifold learning have made advances in utilizing the manifold-based data generation paradigm and opened up dimension reduction techniques for nonlinearly embedded data. But they both generally require a target dimensionality as a parameter, either in form of a network shape in the case of autoencoders or as a number in the case of manifold learning. Assuming the approaches can successfully learn the manifold from the data, the true intrinsic dimensionality is a correct parameter for these approaches. In case they are unable to learn the manifold, that happens likely due to bad assumptions, in which case we argue that involving the same assumption-based bias introduces a better result. In addition to that, even entire algorithms for problems like clustering have been directly derived from intrinsic dimensionality estimates, which can be applied if different clusters have different intrinsic dimensionalities. Related work so far has mostly been focusing on local neighborhood expansion rates, typically by analyzing the distances from a point of interest to its k-nearest neighbors. This concept is based on the observation that balls in d-dimensional space expand in the power of d relative to their radius. If hence our nearest neighbors lie on a lower dimensional manifold, we would expect larger bores around the point of interest to be increasingly sparse. That is equivalent to observing a decrease in density for expanding radii. These approaches can be understood as the discrete realization of Hausdorff dimension and are known under names such as correlation dimension or expansion dimension. As these approaches are measures of distance, they entail the two core assumptions that the data should be uniformly distributed in parameter space and that the embedding into feature space preserves local distances and therefore densities. This is not a complete overview of our related work, which also encompasses approaches like local principal component analysis and others. Yet in benefit of brevity, we focus here on correlation dimension due to its likeness to the well-understood continuous measures like Hausdorff dimension and extensive theoretical and empirical research. Instead of distances as in correlation dimension, our novel approach uses angles, which is motivated by the observation that directions in local neighborhoods are dependent on the local geometry. If the data truly uses all available dimensions, local neighborhoods will be scattered in all directions, whereas directions in lower dimensional subspaces will at least partially align. This concept is showcased in the two plots, where evenly scattered data on the left gets projected onto the entire circle, whereas highly correlated data gets reduced to one direction. Opposite to the argument of densities, this is rather an argument of geometry, where the shape of the sphere projection is analyzed. It is based on the assumption that an embedded disk should at least locally still look like a disk. As can be expected from an inherently different approach, this induces a different set of assumptions. First of all, we do not require a uniform distribution in parameter space, but rather an angularly representative one. That is, solely projections to the hypersphere around our point of interest need to be uniformly distributed. Secondly, we are independent of preservation of distances or densities, but require the preservation of angles in the embedding. This assumption, however, differs only slightly from the more common concept of local linearity. In general, local linearity preserves local angles as long as the embedding does not locally shear the space or if the embedding has a high curvature. Thirdly, the embedding should not induce singularities like self-intersections of manifolds, as the surroundings of singularities in feature space might appear to have a higher intrinsic dimensionality due to the crossing. Although these assumptions might appear stronger, we argue that they are reasonable when the intrinsic dimensionality is used as a parameter for downstream applications like manifold learning, as most approaches in that field make very similar assumptions. On the previous slides, I have mentioned multiple assumptions based on locality. To increase the robustness of distribution-based approaches like the intrinsic dimensionality estimators, observing more data points is generally beneficial. In continuous math, local analysis of curvature, expansion, and geometrical distribution is often performed on infinitesimal small environments, as these already contain infinitely many points and do not introduce unwanted information from farther away. Our data, however, is discrete, and interpolating arbitrarily many additional points does not add meaningful information. We therefore need to observe larger environments, which can result in false observations as we violate the locality assumptions. Choosing the right environment size, that is, choosing a reasonable amount of nearest neighbors, is hence required, but a challenge in itself where we have to balance between robustness and correctness. If we look at the example below, we can see a mixture of noisy points from three one-dimensional manifolds embedded in two dimensions. The circles in this example represent different neighborhoods. In the left neighborhood, where the different manifolds come close to each other, the sampling is geometrically indistinguishable from a two-dimensional space, which obviously does not properly represent the intrinsic nature of the data. Choosing a smaller neighborhood, however, will likely introduce numerical instabilities, as the data is not sufficiently densely sampled in this region. This is an example of how data can be too sparse for proper analysis. Further on the right, we can see a good choice of neighborhood size, as the data is plenty enough to make a good estimation, yet not too big. If we increase the neighborhood size radius a bit, we again observe points from the other manifolds. Especially in the case of the expansion rate based approaches, this enlarged neighborhood would result in way too large estimates, as the density of points suddenly increases largely at a certain distance, which resembles a very high dimensional space. This behavior can also be observed in datasets that are not mixtures of manifolds, as a single manifold can be folded up to behave similarly, like the Swiss roll example on the previous slides. Also, increasing the size of the observed environment can not only increase the estimated dimensionality, but also decrease it, if for example farther away points resemble a line. As the proper choice of neighborhood sizes introduces a challenge in itself, estimators that require less neighbors for a robust estimate are beneficial. The strongest contender in that regard, as it claims to require the smallest neighborhood sizes of any expansion rate based approaches, is the tight-lit estimator proposed by Amsalek et al. But before we take a look at empirical comparisons of the estimators, I would like to explain a bit about what the ABID estimator does mathematically. The theory behind our estimator is directly derived from the distribution of pairwise angles of points in spheres provided by Kai et al. However, obtaining angles practically requires the use of trigonometric functions that are computationally costly. The cosines between vectors, though, are more accessible. We therefore transformed the distribution of angles into a distribution of pairwise cosines. These distributions, however, do not consider angles or cosines between points in themselves. Further, the distribution is only symmetric if points from the entire hypersphere are observed. If one half is not sampled, the distribution is extremely skewed, as there are only few angles above 90 degrees and therefore only few cosines below 0, which is the midpoint of the distribution. To counter that effect, our estimator is based on the second non-central moment, which is equivalent to considering a copy of each point mirrored at the point of interest, and then computing the variance of the cosines. These mirror points introduce the missing angles to make the distribution symmetric. As a bonus, the mirror points do not add information on symmetric distributions, as then the mean is 0 and the variance and the second non-central moment match. The raw angle-based idea estimator of a point x and a neighborhood size k is then simply the inverse mean of squared cosines. These cosines are computed for all different pairs of k nearest neighbors centered on the point of interest x. Unlike the distance-based estimators, this estimator has an upper bound, given by d times k minus 1 over k minus d, where d is the true intrinsic dimensionality. This bound, however, depends on the previously mentioned assumptions. For larger neighborhood sizes, this bound converges to d, but as d and hence a sufficient neighborhood size is unknown in advance, we introduce a second estimator with an upper bound of d. Interestingly, the regularization only requires to drop the constraint of only considering cosines between different points, which even results in a simpler formulation. As the neighborhood size increases, both estimators approach the same value, whereas the raw ABID estimator is strictly larger than the ABID estimator. The difference between these two estimators can even be used as an indicator to whether the neighborhood size was chosen sufficiently large or not. However, we need to keep in mind that we cannot just increase the neighborhood size arbitrarily, as this might interfere with the locality assumptions. But in combination with the upper bound, it makes choosing appropriate neighborhood sizes for these estimators somewhat easier, as approaches related to correlation dimension have been shown to overestimate the true intrinsic dimensionality for too small neighborhoods and underestimate it for too large neighborhoods. In our evaluation, we compared estimates from the angle-based and distance-based approaches on both real and synthetic datasets. When analyzing our results, we made a few key observations. Firstly, the semantics of noise, outliers, and surface points vary largely between distance-based and angle-based approaches. In the example below, we computed estimates for both points scattered in a two-dimensional plane and a single point lying next to it. As for the points in the plane, both approaches agree on a rather two-dimensional subspace, as can be seen from the histogram on the right. Note how the angle-based estimates are cleanly cut off at 2 dimensions due to the upper bound. The single point, however, results in a Locality estimate of about 10 for the distance-based approaches, whereas the angle-based approach estimates an intrinsic dimensionality of 1 and a bit. These estimates are represented by the dashed lines in the histograms. The distance-based approach does not take local geometry into account and solely observes a sudden increase in density at a certain distance, which would be expected from a higher dimensional parameter space. The angle-based approach instead observes that the neighborhood lies in a narrow cone, which is best explained by a one-dimensional manifold. Where unrelated noise points appear high-dimensional in distance-based estimates, they can appear very low-dimensional in angle-based estimates. A similar yet weaker behavior can be observed near the limits of the distribution. Distance-based approaches are generally not too affected by observing points in only one direction, whereas angle-based approaches can decrease near the limits, as for example corners of distributions have geometrically less degrees of freedom than points in the center. Secondly, we analyzed how well the different approaches can separate mixtures of different dimensional manifolds. For that, we sampled hypercubes varying from 1 to 5 dimensions and linearly embedded them into the same 5-dimensional space. The displaced histograms showed the distribution of estimates depending on the approach. The 2 histograms on the left are distance-based approaches, the first being the Hill estimator and the second the Titleist estimator by Amsalek et al. Mentioned before. The third histogram belongs to the ABID estimator. The angle-based approach clearly separates the single manifolds cleaner, visible by the higher spikes and the shorter tails. Please note that the histograms of the distance-based approaches have been cut off to the right and have a longer tail than displayed. The separation of different dimensional manifolds can also be used to separate out a large amount of unrelated noise points, as these can form a high-dimensional manifold when numerous enough. Thirdly, we analyzed how the different approaches behave on nonlinear embeddings. For that, we computed estimates for points sampled from fractals, among other things. The benefit of sampling points from fractals is that we have a sort of ground truth from math, that is, the Hausdorff dimension. The Hausdorff dimension of the Koch snowflake, to the left, is about 1.26. As the correlation dimension related estimates are highly related to the Hausdorff dimension as well, they mostly agree upon that value. The angle-based approaches, however, give a higher estimate of 1.7 up to 2. That increased estimate can be explained by the many non-linearities at each corner of the Koch snowflake, where the preservation of local angles does not hold. Accordingly, samples of the Koch snowflake locally appear to be higher dimensional. Although mathematicians would likely agree that 1.26 is a true intrinsic dimension of such a dataset, we argue that an increased estimate might yet be beneficial. As mentioned before, different applications like manifold learning and autoencoders also make various assumptions on the nature of the dataset. Learning the exact shape of the Koch snowflake from a sample is difficult at best, as the data is indistinguishable from a sampling of a two-dimensional belt, given such a set of assumptions. As a parameter for downstream applications, it might thus even be beneficial to give an estimate based on geometric shape, even if it is distinct from theoretical ground truth values. In a fourth analysis, we tried to evaluate the robustness of the different approaches under varying neighborhood sizes. Choosing the right neighborhood size for reasonable estimates is not trivial, as it has to be large enough to get robust estimates, yet small enough to not break any locality assumptions. To visualize the behavior of the estimators under varying neighborhood sizes, we computed estimates for all points in a dataset at different neighborhood sizes and plotted one trace for each point. The traces were then color-coded along a 3-color gradient in the order at 200 neighbors. Straight horizontal traces thus correspond to points with very stable estimates that change only little when varying the neighborhood size. If the colors are mixed a lot at a certain neighborhood size, however, the order of estimates varies largely from the estimate order at 200 neighbors. As can be seen from these plots, the estimates of the angle-based approaches, and specifically of the ABID estimator, are less sensitive to changes in the neighborhood size on a per-point basis, and also have a more stable overall behavior as compared to the distance-based approaches. The order of estimates is mostly stable between 150 and 300 neighbors, which is a far broader window than in the case of the distance-based approaches. To back up the visual analysis of these plots, we computed both Spearman's and Pearson's correlations on neighboring orders of estimates. Both correlation coefficients support the claim that the angle-based approaches are more stable under varying neighborhood sizes. Hence, the choice of the neighborhood size does not need to be so specific, and the overall distribution starts to stabilize at lower neighborhood sizes, which might be a necessity to meet the locality assumptions in sparse datasets. After the empirical analysis, a few key differences between and challenges for the different approaches arise. For many datasets, we observed different estimates from the distance and angle-based approaches that among themselves, respectively, mostly agree. We expect these differences to stem from the different assumptions that lead to the formulation of the estimators. Approaches based on expansion rates are inherently hindered at detecting singularities or self-intersections, as these, in the simplest case, double the number of neighbors in a certain radius. This scalar factor does not impact the exponent of the expansion rate. Our angle-based estimators, however, cannot differentiate between self-intersections and additional dimensions, which leads to increased estimates. A similar behavior can be observed in the case of locally nonlinear embeddings and strong curvatures, which again does not affect expansion rate-based estimates, as these effects are of a purely geometric nature. Besides that, we observed a clear difference in estimates of outliers and unrelated noise points. The different approaches give clearly different results, however none of them appear unreasonable. The angle-based interpretation of outliers as points that span a low-dimensional subspace is somewhat more in line with the very geometry of the data, yet the very high estimates of the distance-based approaches makes them easier to spot, which is a benefit in itself, even if we probably do not need a much higher dimensional mechanism to explain the noise. At last, some of the differences can probably be explained by the choice of the data. In some cases, there simply is not enough data to get proper estimates in sufficiently small environments to allow for nonlinear embeddings. And, as in any task-around data, the data quality can be an issue as well. At last, I would like to summarize the key points of this talk. First of all, intrinsic dimensionality can be considered a measure of data complexity and is based on a generative assumption that tries to explain the nature of datasets. Prior work in this field has mostly, but not uniquely, been focused on expansion rates of local neighborhoods under the general term of correlation dimension, which is strongly related to the Hausdorff dimension. We introduce a novel approach based on angles that overcomes some of the struggles of distance-based approaches while introducing others. In our experiments, we observed the angle-based estimates to be more robust against noise, mixtures of manifolds, and varying neighborhood sizes, while producing seemingly tighter estimate distributions. However, the angle-based definition is further away from the theoretical background of fractal dimension and introduces a different set of assumptions that may arguably be somewhat closer to applications like manifold learning. As both the assumptions and semantics of distance and angle-based approaches vary, the two approaches are complementary. Further research on combinations and interactions of both approaches may lead to an improved insight into our datasets. Thank you for your attention.